Okay, so continuing on, let's look at that graph that we made and talk about that the domain is all real numbers, or you can write it as negative infinity to negative infinity. The range was 0 to infinity, not including 0, because you could never get a y value of 0. The x-intercept was 0, 1, and there's no, oops, I did that wrong. There's no x-intercept. And the y-intercept is 0, 1. So you can see that from the graph. The end behavior is as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y gets closer and closer to 0. So since this function is always increasing, we know it is 1 to 1 from the previous section. So that means it has an inverse. Okay, so that's the thing that we get from looking at the graph and what we talked about before with the always increasing. So lots of quantities grow exponentially. Money in an interest-bearing account, debt, time for a wound to heal, the spread of rumors and viruses, endangered species recovery, learning, and lots of other things. So it's a really, really useful function. So all of the transformations we learned apply. So let's look at some examples and see, and we'll do this in class together, where we match the graphs to the equations. See if we can figure those out. So the other thing you need to be able to do is look at a transformation and say what happened. So here we can see, here's the exponential function is happening and then subtracting 2. So it's order of operations. The exponential happens and then minus 2. So this shifts down 2 units. And this one, you can see that the plus 2 is happening to the x before the exponential function is happening. So this is going to shift 2 units left. And then let's talk about these other two together. So objective 3 is about the number e that's on your calculator. So it's an actual number, and it comes from the Swiss mathematician named Euler. It's pronounced like a German word, Euler. And so that's in his honor that the letter is called E. That's this number. So it's defined as the number that this expression, 1 plus 1 over n to the power of n, approaches as n gets really, really large. In calculus, we write this using limit notation. We say the limit as n goes to infinity of this quantity, 1 plus 1 over n to the power of n, equals e. So you should be able to find this number on your scientific calculator. And you do need a calculator that has an E button, and then we'll use our calculators to make sure we all know how to do this. And then the transformations work the same way with the E, so we'll do these two examples together in class. And then let's solve some simple exponential equations. So the thing that makes them an exponential equation is the variable is an exponent. Okay, so that's what makes it an exponential equation. So there's a property of exponents that seems pretty logical, that if I have 2 to the x and that equals 2 to the y, then it just seems to make sense that x would equal y, right? So if we can figure out a way to write our problem with the same base of a, then we can say the exponents have to be equal. So that's kind of the trick here. Here I see a base of 3, and this doesn't have a base of 3. So I think, is there a way to write 81 with a base of 3? And there is. I can write it as 3 to the 4. Well, now I can use that property that says, well, then the exponents must be equal. So negative x must equal 4, and x must equal negative 4. So that's how I can solve for the x. Okay, so then let's do a couple more of these in class together. And then the last couple are finding an exponential function with a graph that's given, and find an exponential function with this horizontal asymptote containing particular points. So I'd like to do those together with you in class.